So, hi everybody and welcome back to our weekly Raspberry Pi Pico simulator stream. Please let me know in the chat if you can hear me and see me and everything is fine. And then we will be able to start with our weekly hacking. While I'm waiting for your answers in the chat, I will also start screen. Okay. Yep. Now you should be able to see my screen. Let me know if you see and if everything is fine, so we can continue. Hey, okay, perfect. I'm getting your chat messages. Works like a charm. Perfect. So hi, Andreas and Kati. Good to see you here. So it's been a week, and let's see where we left off. So last week we were working on this UART. So we were trying to get this piece of code to run on the simulator. And we almost got there. So this is the code, the demo program from the Pico examples project. And this is the assembly code that was generated when we compiled this program into the Raspberry Pi Pico. And let's go back to the project. Here is the project. And last week we implemented a bunch of registers, and we got a little confused by all those flags and how to implement them correctly. But this week I went back and checked the code, and it seems like we did it fine. So bravo to us. Anyway. Let's see. So we had this code, we called it randlink, that would load this compiled hello UART program, and then basically this is one of the UART registers, the flag register. I will give it a pretty name in a few moments, so we won't forget what this magic number means. But this is one of the UART registers, and we set it to return 0. And then we just set the program counter to start from 370, that's here. Or no, 370, not line 370, but address 370. That's the beginning of main, and it would run a branch of instructions and print the address of every instruction that we execute, so we can see the flow. And this is actually from last week. We had this read from invalid memory address. Let's run it again just to make sure that everything is still working. And yes, so we have these strange reads. It coming from the instruction in this address 3C6, so 3C6, yep, here we go. So we have this instruction that loads something from R2, so the address pointed by R2 plus 24 into R3, and this is the resulting address. So this is the address that we calculated, and R2 should contain this value, 4OC. What's in 4OC? 4OC is this value. So it should have this address plus 24. And this is obviously not what this is like. It's a different number. It's not the same number. It's 46 something, and this is 40 something. So we'll have to figure out how did that happen. So basically we are going to sort of start debugging the program. What we will do, we will just print the value of R2 in in each of these instructions. So we will see, let's print it in hexa. We'll see why it doesn't get the right value. So yes, so for some reason R2 is getting it's getting the correct value. I think this is the value we expect it to have, right? But at this point, at this instruction, it somehow changes to something unexpected. So let's see what's at 3BE. 3BE x 3BE. Yeah, 3BE comparing R3 with 0. Oh, sorry. So it's probably so yeah, we print the value after executing the instruction. So it's the instruction before. So loading R2 PC from this address. So we are loading this address into R2. Okay, so basically it should be loading the same value again, but for some reason this load instruction doesn't give us what we want. It gave us some garbage. So let's see what's the reason for that. We are doing the LDR instruction. So this instruction, let's take a look at our implementation of the LDR. So we have two versions, two variations, and then so we are reading unsigned integer from the given address. Let's just console log the reading from where the address we are reading from to see if we are reading from the right place. And at this point, it might be worthwhile to introduce a new unit test to test that. I'm not sure about that yet, but let's give it a go with this approach for now. So let's see. So this is where it gets wrong, and it's reading from 408. Why is it reading from 408? Reading from 408. So, yep. So first of all, this reminds me that I got a comment in GitHub. So somebody actually opened an issue on GitHub, and for some reason my internet doesn't want to load GitHub. It's a bit tired right now. Interesting. Let's check my internet connection. Should be fine. If you are seeing any problems with the stream quality, please let me know, because it seems like my internet is kind of dead. Anyways, while I'm waiting for that to load, let me see. Let's try to switch internet connection again. Okay, maybe now it will be better. No internet. Great. Okay, finally. Okay, so I was telling you about this nice person who left a comment, and what he said is that instead of increasing PC after the instruction, we need to increase it before the instruction is executed. And we had a short discussion, and then I found this in the manual. It says the PC value of an instruction is its address plus 4 for a thumb instruction. So we are working in thumb mode. Thumb is like the 2 bytes per instruction. So whenever we need to look at to read from PC during an instruction, we should actually add 4 to the address that we are currently executing. And that actually explains a lot, because if you remember, we had to add this plus 2, and we weren't sure why. And now we know why, because basically we are adding an extra 2 here at the end. So 2 plus 2 is 4. But right now we also have another instruction like this. LDR is also reading from an address relative to PC, and we also added 2, but we should have added 4. So luckily that nice person actually helped us here even before we knew that this would be an issue. So I'm going to take his suggestion and just move this to the top, and then so before decoding the instruction, let's increment the PC, and let's just get the text running again, because for some reason they aren't. And now let's so now it makes sense to add 2 to PC at every point, and now we can see that LDR actually fails, which makes sense because now I think it does the right thing. It does what it should do. It reads from PC plus 2. Now it says that we should align the PC, and I think that's what we tried to do here. Like, this was our attempt to align PC, but there is like an algorithm. It says just end it with this value to force it to be word aligned. So instead of like coming up with our own, which I think it's basically the same what we did here and ending with this value, let's just do what the manual says. And okay, so now the test here is failing. Let's check why. So let's open this to the side and see what's and see what's going on here. That was LDR, and we are loading, so we are trying to read from 148, and our instruction is PC plus 148. So obviously that should be current instruction plus 4 should probably be, and then we are filling the next few bytes with 0. So let's see. So if PC is 0, then we have 0 plus 4 plus this offset. So this is the value, and we need to no, we need to byte align it, but it's already. So basically this instruction should really read from this memory location. Then we need the following memory locations to be 0. Okay, so now we fix the test and the instruction. Now it does what the manual says it should do. We are reading probably from the right place. And after fixing the test, it would be a good idea to run the program again and see if we are still getting those weird reads. And no, actually it's reading from the right location. It's reading from where we expect it to read from, which is great. So thank you. What's his name? Che Guevara. Okay, thank you, Che Guevara from Poland. You helped us a lot here. And I encourage everyone here, just leave your feedback. But by the way, there is a nice explanation here that Steve from the UK found about why it behaves this way, why it's always PC plus 4. So if you're interested, just read this, open this link, and it explains the historical reasons for that weird behavior. Anyway, so at this point, we have the program. Most of the stuff is implemented. There are a few instructions that we still don't recognize. Let's see them. So 3D0, what's a 3D0? 3D0, A add S. And then I guess these are also not implemented. So yeah, all the next few. So 0, 2, 4, 6, 8, A, DC. So basically all this. And interesting, we don't have this. Oh, we have LDR, we don't have LDRB. So yeah, we have a bunch of instructions to implement. So these are most likely going to cover the most common arithmetic instructions. So they will let us execute a bunch of new code. So I expect that after implementing those and probably a few more, we'll have enough enough instructions to execute most of the code here, or at least I like to think so. That kind of optimism, that's what keeps me going. So let's take a note of all the instructions that we want to implement, and let's start with ADCS. And while we are doing it, I'm actually going to start improving the code for the tests, because I don't like these magic constants, and I think we can do better. So let's start with ADCS. Let's go to the datasheet that was here. Instructions, where are you? I think it's A5 or A6. And list of instruction, ADCS, probably ADD, or there is no ADCS, right? Not that one. By the way, hi to Masum Eslan. Did I read your name correctly? Hi to you too. Okay, so add, but ADCS, what does ADD? Oh, ADCS, yeah. Add, just adding numbers. Okay, perfect. So we are getting register, and immediate value. And that register is optional, so we can either get 2 registers and immediate value, or just a register and immediate value. Let's see which variation we have here. Just 1 register, so that's this variation. And then we are 0 extending this to 32 bits. So basically just adding zeros, nothing interesting. And then we are calling this add with carry that we had last time, and updating the flags. So okay, let's do this. So the first thing we are going to do is just create a test case, and as I told you, I want to make it a bit more friendly, our test. So it should execute, what was the name of the test? ADCS R1, add 1 to the value of R1, I guess, instruction. And then what I'm going to do here is just set up everything. So we need to, we'll need a bunch of assertions. So basically this is the opcode, and then this is what this opcode means. And we want, let's say, R1 to have the value 60, and then after executing this instruction, we want it to assert that it's 61. So it actually added 1 to this value. Okay, perfect. Hey Tony. Okay, great. And executing, adding, perfect. So the test case. And before we jump to, and let's see. So the result is not negative, the result is not 0, there is no carry, and I guess there isn't any overflow. I will have to check about this overflow flag again. You know what, let's make it a bit more interesting. Let's do it like adding to 1 to all f. So we expect it to actually be 0, and then negative is false, but the result is 0, and I think there was a carry. So we'll actually check some of the logic for the flex as well. And before we jump to implementing ADCS, what I would like to change is I don't like this use of magic constants. So we'll start creating our own mini assembler that will help us keep the test clean. Let's create a utils directory. No, a directory, not a file. Not a file directory. And let's call it assembler. Assembler.ts. And then we'll just create a bunch of that's opcode ADCS, and it gets RDN number and IMM8 number. Let's call it ADCS2 because there are like two variants. And then what it does, it basically just encodes this instruction. So return ADCS is like, these are the high bits, so this one t. I don't know if it's correct, but we'll check it in a moment. So, and then we need to take IMM8, and just to make sure it's not overflowing, so it should be. And the RDN is 3 bits, right? So yep. So let's and shift left by 8, and this should have we can just shift left it, so 11. That would be easier than counting zeros. And then instead of like encoding this knowledge about the encoding of the opcode in the test case, we can just create a test case for this code, opcode assembler.spec.ts, and then we can expect describe assembler, and we should create a test case. It should correctly encode an instruction. Then we can say expect opcode ADCS with, let's say that was, I think, R1 and the value was 1, right, in the original test case. Yeah, R1, and so this should be encoded to equal this. Oh, well, it doesn't work. Why doesn't it work? What did we miss? So this is 00110. This is 3 bits, and this is 8 bits. So let's print the let's start reprinting the. Oh, thank you, Mark. Hey, nice to see you. Okay, let's see what do we have here. We have this 1101, so 110, and then why do we have a 1 right after it? It shouldn't be a 1. Let's see this in hexadecimal for a moment. Yeah, so the lower byte should be 1, that's fine, but then this byte, why is it 7? Something is wrong. Oh, of course, I used ampersand instead of ampersand, and now it works. So use the wrong operator. Thanks God, there is a test for it. So now I have this, and now I can use this in the test. And the nice thing about it is that now the test is a bit more readable. And to make it even more readable, let's change this constant to R1. And I think eventually we will probably, at some point, we'll create something that can actually get a string like ADCS R1 and return the opcode. But for now, I think this is already a major improvement, and it makes the tests more readable. And I don't think I'm going to go back to all the existing instructions and change them right now, but for the new one, we can use this approach. And then we also don't need to repeat like the instruction in the comment to make it clear and keep them in sync. So one less thing to worry about, and let's do the ADCS now that we have the test case for it. So ADCS, where are you? So just before, so that's ADCS encoding D2. And we check the opcode. It should be these should be the highest bits, and then we extract the IMM8. So we don't need this shift, and we also extract what was it called? RDN is the opcode. Opcode shifted by 8 and 3 lower bit, and then let's see, we need to add these two numbers without a carry and update the flex. So let's start by calculating the result. The result is just the value of IMM8 and this dot registers RDN, so adding the two values, and then I think we already have a bunch of bunch of like those to help us with calculating the result, the flags. So yeah, so we have these two to check for the carry and the negative and the 0, and then for the carry we should just check if the result is basically too big to fit in. Yeah, if it's greater than this value. Okay, I think, yeah. And then finally we need to oh, of course, we also need to store the result, and then this will probably pass, or maybe not. Let's see why. The result should be, oh, I'm missing an F here. So yeah, now the test does make sense. Okay, so yeah, 0 shouldn't be checking the result. It should be checking if result and yep. And I just need to implement this v flag. Let's see how it's implemented. Add with carry. So I think we checked it last time. Overflow. If carry in, oh, that's if x is not y. So let's just see what happens here. So basically overflow is if that's overflow. So overflow is if sint result is equal to signed sum, then fs, else, then 0, then else 1. So sint result is interpreting the result as a signed integer if it's equal to the signed sum. So in which case it won't be. So I guess this means like if we had minus if we had this value, So basically that's the lowest value that could be. And then we, I think, yep, that's the lowest signed 32-bit value. And then we added -1. Then we would go past below the lowest value, and we will overflow basically this value is actually encoded as like this value. So we would overflow, and the result would actually be this value, which is the highest signed 32-bit value. So in this case, for instance, we need to set overflow to true, because in this case we overflowed. So in practice, that would be if we overflowed if the result is just too big to fit in, I guess. So, yep. So if, yeah, I think the test we did last time would actually do the trick. Let's see if that works. So so instead of value, that would be let's call it left value. Okay, so if left value is greater than 0 and we add a value that is greater than 0, then we expect the result to be greater than 0. And I'm doing this to turn the result into a signed 32-bit integer. That's something that we did last time, or just a quick JavaScript way to convert a 32, any number. Basically, the numbers, I think, are stored as double precision values in JavaScript. So that's how you force JavaScript to convert them to a signed integer. So for instance, if I do this, so this is this number, but if I do this, then that's -1, because it looks at it as if it was a 32-bit signed integer. So if I'm adding two positive value, then I expect to actually I can just use this how do I check the sign of the result? Yeah, so if they are positive, if I'm adding two positive values, then the result should definitely be positive. And then I can do the other check. If I'm adding actually, we had this, we found this result last time. Maybe it has a shortcut for us. Overflow rule for additions. Okay, cool. If a plus b equals minus c, or minus a minus b equals plus c. So yeah, if both are positive, then and the result is negative, or if both are negative and the result is positive. So let's do that. So let's see. So if left value is positive, and left value is actually right now it's 32 bits and unsigned, so let's turn it into a signed number. So if it's positive, and to turn this into a signed number, I can just check if it's, so this is way to check. This is just 1 byte, so I could sign extend it, but that's a quicker way to check if it's positive. So both of them, let's move it away for a moment. So if both of them are positive, and I'm just adding a bunch of parentheses to make sure I don't get the order wrong. And then the other thing, so if this is positive and this is positive and the result is negative, or this is negative and this is negative and the result is positive. Yep, I think that that seals the deal. And we have the overflow, and let's just add another test case to make sure that the overflow does what it should do. Tony says that we could only take the signum shift right 15. Where is the signum? I'm not sure. Signum is like there is a sum, like maybe you meant to sign sum. Anyway, I'm not sure what you mean, so if you want to elaborate, then yeah, please feel free, and I will try to do that. Otherwise, let's create we need a test case anyway, with and set the overflow flag correctly. So basically, if we have let's say we had an example, so if we have this value, which is basically -1 signed, and then we have, actually we can set it to -1. The type of this array is unsigned, so it will be automatically converted. So we had oh, that wasn't -1, that was minus many, and then we add 1 to it, right? No, we had -1. Then we expect the overflow to be true and negative to be false. Oh yeah, we don't need to, so adding -1 to this. So we expect the value to be this maximum int, and it doesn't. Let's see why in a moment. And it's not negative, there is no 0. There is no carry, I think, or there was a carry. Yeah, I think in this case there should be a carry, and there should be an overflow. And let's see why we get a strange result here. Expected this, received that. Yep, that's the right number of zeros. Let's print out the result. Let's just focus on this test so we don't get any noise. So this is what it got. Let's print out the two values. Left value is this. Yeah, I think I'm seeing what the problem is here. Yeah, I think yeah, that's definitely not a -1. So something is the signed sum and the unsigned sum is not the same, because let's see. Yeah, maybe we can't have we are not sign extending it, right? So I think we are 0 extending this value, so it means we can't have a negative number here, if I am getting it right. So this test can't happen. So the only case that would cause an overflow is probably adding 1 to this value. So adding 1 to this value, and so it turns out the test was wrong here, because we can't really have a minus here. It won't be interpreted as a minus if I got it correctly. And then we expect this and this to equal this, and then this is negative. Yep, it's not 0, and we don't have a carry in this case, but there is an overflow. Great. So yeah, so that's with EDS. We got EDS ready, and now we can go on with the next instruction, and that would be subs. And I guess it's very similar to EDS. Let's take a look. Subs. Sub register, and that's not the one. SP minus immediate, that's not the one as well. Oh, sub immediate, yeah, that's what we need. And again, we have this encoding with just one register, so it's pretty much the same, I guess. 0 extending it, and then add with carry. Yep, cool. So I think we have okay, so basically I think this condition is actually not required for ADCS, because this value it can't be like negative, so that's a mistake to include it. We should remove it. We should only keep this one. Okay, so let's implement add the test case for subs, but before that, let's create the assembler for subs. Export function opcode subs, and that's also encoding 2. It gets an RDN and IMM8, and it's pretty much the same as EDS, but I think only the bits are different, right? Yep. 0, 1, 1, 1. Cool. And let's create a test case real quick. So we had an instruction here, and that's the expected opcode. Subs. Let's actually create those as constants to make it a bit more readable. 1, 1, R3 equals 3, and import this function, and then subs R313 should be equal to this, and subs R313. Okay, and it passes. Great, we have this new opcode subs, and now we can use it in the actual test case. So subs, it should execute subs. That was actually, we can now, we are no longer we can go with any value that we want, because we have this freedom of using whatever opcode, since we have this an easy way of creating the opcode. So let's remove 10 from R5 just for the sake of it, and then let's just copy this body from add, because it's pretty similar. Okay, so we are taking R5, and let's say R5 has 100, not hexa, just 100, and we are removing 10, and the opcode should be subs. Cool. And then we expect the result, R5, to have 90, and that's not negative, that's not 0. We didn't have a carry, and we didn't have an overflow, so that's a super simple test case. And okay, let's implement subs. So subs is basically, let's just move it to the right place, and we also need an else here. Okay, subs and then else here. If the opcode is 111, then the decoding is the same, and then the result is just this minus this. I think we actually did something very similar in CMP last time. Yeah, we need to convert it to if we convert it to basically, I think we can just go copy the code we got here, and oh wait, with CMP we sign extended. Do we need to sign extend here? No. I just double check that we didn't have a mistake with CMP. Oh, we actually did. It should have been 0 extended and not sign extended. Right? IM8, that's IM32, and we are notting it. So we shouldn't have 0 extended it here. That's a mistake. Sign extended. That was a mistake. Okay, good. Another mistake found, another bug discovered and killed. Okay, and then let's hope this logic is good. We can just use it here. Copy this and let's value. We call it value here. And it fails. Why does it fail? Because and the result should be -10 because value is 0. Why is value 0? Which register? Oh, right. We need to read from R5. And now this works. Except for why do we have a carry here? Interesting. Yeah, I guess that this means, yeah, I think if I remember correctly, so subs uses add with carry, and add with carry with not and 1, they had this note that if like this is the pattern and carry in is 1, then carry out is 1 if the unsigned overlap, that is if x equals or greater to y. So in this case, x, the left argument, is equal or greater than 10, so it should be true. It makes sense. Let's maybe do one more, just to check this tricky overflow flag. So basically, if we take a very negative or very positive number and very positive number, like let's change it just for the sake of it to be R1 this time. R1 instruction, and just remove 1 from it, but let's make it the smallest possible negative value. So R1 will be -1 minus this, and then adding subtracting 1 from it should cause an overflow. The result should be this, just the largest possible integer, but it's not for some reason. Let's see why. What did I miss? Yeah, it seems fine. So, oh yeah, I'm comparing the wrong register, but it says that we didn't have an overflow. So first of all, IMM can't be less than 0 here because we didn't sign extend it, so we don't really need that flag. And then basically, if value is less than 0, but value want to be less than 0 since it's signed, I mean it's unsigned, so we need to convert it to signed, and now the condition is fine. And then we can go back to CMP and fix the logic there, because that wasn't this, it was this one. Where's the logic? Yep. So we can go back to CMP and fix the logic here, because this one, because again IMM isn't oh, actually we don't need to do this here because we already converted it to signed here, so we don't need this, but we still don't need the second condition because IMM8 will always be positive by definition. Cool. Okay, cool. So we have the second instruction that was far faster than the first one, and then we have this NEGS. So let's take a look at NEGS. NEGS. NEG is equivalent to RSBS. Whew. Free UAL synonym. What's UAL? No idea. Anyway, we can just implement RSB. RSB is reverse subtract register from an immediate value and write the result to the destination register. Okay, so it's basically doing there is a const here, but I don't see. Oh, okay. So it's probably, yeah, it's probably just another way to represent neg. So it's getting this is the opcode. It gets to registers, and then the result is add with carry, not rn. So basically, what's IMM32? It's just 0. So it does. Okay, so basically this is a very long way to say that we are doing bitwise not to this register, right, to rn, and then adding 0. Okay. Oh, right, and 1 for the carry. So that's basically 2 complements, probably. And then I guess we are just checking the flags. Let's figure it out in a moment. Okay, but let's create a test case for this first of all, or maybe first of all, let's create encoding. So NEGS. Let's just call it just as in the datasheet. So opcode RSB. Is there like another RSB without? No, there is always RSB with immediate. Okay, so RSB is getting RN and RD. Actually, RD and RN. To stay consistent with the order in the datasheet. So RSBS, RDRN, and this is the encoding. So return this. And then we have R and is next, and then we have RD. Okay, and let's create a test case. So assembler spec, and this time we have it's RSBS. RSBS with R0 and R3. R0 and R3, so that should equal this value. Okay, so let's just import, and it should be R0 and R3. Let's just define R0 to be 0. Huh, what's that? And it doesn't fail, and it doesn't pass. Interesting. Something happened to the test runner. Let's see what's going on here. Yeah. I guess something threw it off. Let's try just to make a small change here and save, or just restart the test runner altogether. Yep. Okay, it passes, great, and now we can create our test case. So basically, so that's NEGS, but it's actually RSBS, so that would go here probably. It should execute RSBS. That was NFS R0 R3 instruction, and then, just as we did last time, copy the. We no longer need it here. Just let's leave a notes here. It's also called NEGS. This instruction is also called NEGS. Okay, and now we can create the implementation and check it. Opcode. We need to create a Raspberry Pi class instance. Okay, opcode RSBS R0 R3 whatever, and then we have some value in R3, and then we expect R0 to equal minus this value, so basically the negative of it. And then so let's see, negative is true and 0 is false. And did we have a carry? Can we have a carry here? We are doing this thing where we are adding 0. So add with carry, let's check it again. Add with carry, carry in is 1 if x greater or equal than y, and it will always be true unless, yeah, we always have here carry, because whatever we have here, x is x is like, where is x coming from? Is it signed or unsigned? Let's check it out. So carry out if unsigned in result equals unsigned sum. So yeah, so since we are adding 0, I guess the unsigned sum is just this plus 1. And the only way we could have carry is, I guess, if this. So the only way we could have carry is if this value, if x is -1, I guess. No. Yep. Yeah, if it's all f's, then we would have carry when adding 1. And for the overflow, let's start in. So this would be false here because it's not all f's. And for the overflow, we would overflow if the signed int of the result is not equal to the signed sum. And we are always adding 1. So again, I think it would only overflow on the edges. So maybe on the largest possible integer. That would be the only case we have an overflow. So there are like two values that would cause, one value that would cause carry here and another one that would cause overflow. So it should be false in this case. And let's implement the instruction. So it's pretty similar to those ones. So let's just copy this one. Put it here. Add this else. And let's check the opcode. The opcode is this thing. And then the code registers. So there is no IMM8. There is RN and then RD and RD. Cool. And then we have just result is basically minus registers. So let's just value is register. Let's convert it to a signed value. This dot registers RN, right? We are reading from RN. Yep. And then RD gets minus value. And let's see. So it's negative only if the original value was positive, then the result was negative, it would be negative. It's 0 if, actually let's write this way. The result would be 0 if the input was 0. There would be a carry only if the value was max int, and that's actually -1 in this case because it's we converted it to be signed. And there would be an overflow if the original value was the maximum value of unsigned int. And the last thing, we should just update the comment, and we got another instruction. Cool. Okay, LDRB finally relaxing from the flags. What does it do? Loads register byte, load a byte from memory and write it to register. Just like LDR, I think we already have LDR, but just 1 byte. Oh, we have LDR short, so it should be pretty similar. But as usual, let's start with creating this encoder, this opcode function. And let's keep those sorted as well. So we have in opcode LDRB, and it should start with this magic bits, and then we have LDRB IMM5, so RT, RN, and IMM5. Cool. And then we have like IMM5, and that's 5 bits shifted by 6. And yeah, I think next is RN and then RT. Cool. Let's check that. Let's make a test case for it. Okay, opcode LDRB and LDRB. What did we have here? That was LDRB R0. R1 and 0, so R0, R1 and 0 should equal this, and it passes. So nice. So we have the encoder for this instruction as well, and then we can use it in the test. So we already have a test case for LDRSH, and I think it should be pretty similar. Okay, LDRSH, and then we have LDRB, and in this case it was like loading. It doesn't matter, we can use whatever registers we want. So let's use let's be original, R4, R2 plus 5. Okay, let's just make sure there isn't anything, we are not aligning anything or something like that. So add is always true, so we are adding it to the value at Rn, and then address if index. What's index? Index is true, then it's address offset. Okay, we are 0 extending the address. What does 1 mean here? 232, but yeah, from the base, and immediate offset, load byte from the memory. Let's take a look here. Offset addressing, nothing too interesting, I guess. Yep. Okay, so we are loading. So that's opcode LDRB with R4, R2, and 5. And let's say that R4 contains this address, the start of the RAM. Yeah, we are loading from R2, and then SRAM, this one plus 5, let's say it has 66, and let's just put something on the subsequent byte just to make sure it doesn't get loaded, and we expect the result R4 to have 66. So basically we expect this value to be loaded into R4 but not to be affected by this value. And let's just ensure that it doesn't do anything. No, it doesn't need to update the flags. So nice. And now we can just implement it. So these are like this is like the prefix for LDRB. Actually, it should come before LDRSH, alphabetically speaking, and same goes here before LDRSH. Cool. Okay, LDRB, immediate LDRB, opcode. Did we get an opcode? 01011110 0101. 110. Okay. Interesting. Didn't get into 0 1 0 1 1 1 0 0 1 0 1 1 1 0. Should have been. Oh. So why doesn't it execute this? Why does it get into this if LDRB? Huh? Are we looking? Oh, yeah, that's the wrong LDRB. There are two of them. This is the one we are interested in. LDRB immediate. And so that should now work. Then we have the registers. So IMM5, RN, RT, RT, RN, and IMM5 is just opcode and 1F, so 5 bits. And this is the address, RN plus, what did I do here? No, I didn't want to change this one. I wanted to change this one. RN plus IMM5. And do we need to Stein extend? No, I think we don't need. Wait a moment. This is not the correct instruction. LDRB. Okay, this is the right one. Let's see, we are 0 extending here, so no sign, and 0 extending here as well. So no sign extend here, just read uint 8. And I think we haven't got read uint 8 yet, so let's make one. Let's create it. Just reading uint 16. 32 actually, and returning the lowest byte. Okay, so we have this implemented, but for some reason the test isn't passing yet. Let's see why. LDRB. We are not getting into the if. Did I get the opcode wrong? LDRB register, yes, I got, no, LDRB immediate. Yeah, 0111, and that's not the one, I got it wrong. Okay, okay, perfect. The test is passing, so we have another opcode, but we did somehow kill LDRSH. What did we change here? Oh, yep, RM. That I mistakenly changed this while trying to edit LDRB. Anyway, now we are fine, and 2 more instructions to finally get the code to run. But let's just, you know, for the sake of it, while I take a sip of my tea, yeah, we can see we still have these 2 missing instructions, but other than that we are pretty much fine. Actually there, oh yeah, that's the same offset. No, that's the same one, but what's it? 3D8. 3D8, what do you hold? 3D8. 3D8, that's LDRB we just created. Did I forget to save or something like that? Interesting. Why is it claiming that LDRB is not implemented, even though we just did? We'll have to look at that in a moment. But we do have that. Yeah, we just created it. Okay. But we do have this 3DC, which is maybe. We have CMP, don't we? CMP. We do have CMP. So I think, oh, yeah. Now I get it. So we added 2 to the value of PC. So now this error message shows us the wrong address. So maybe we can do it like that. Let's const current PC. I just save it, and then if we need the or maybe let's call it opcode PC, and then if we need a PC back, we can just print it. Use this one. So now we'll get the correct offsets in the debug prints. And yeah, it says 3D6 is not implemented and 3DA. So what's a 3D6? It's, yep. So that one. Oh, why didn't they just copy the whole line? So we are missing this one and probably that UXTB. Yep, and the UXTB is also missing, and we already have CMP. I don't know why I copied it. So we need the ADCS. What does ADCS do? Probably adding with carry or something like that. ADC. Yep, add with carry. So it should probably be super similar to add. Even though we only have the encoding that adds an immediate, so we'll need to create that. Anyway, let's first of all create the assembler for this. So function, copy this, ADCS, and it has RD, which is implicit because it's always the same as RN or RM. Yeah, RDN. So it's the same as RN, so RDN, and we are adding an RM to it. RM. Okay, and then the encoding would be this long string of bits shifted by 6. 1 ta 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 ta. Okay, and then RDN, and then RM. Let's just make sure that no, RM and then RDN. And this should not be fixed, shifted by 8. It should be shifted by 3. Cool. Now we can create a test case. So ADC. Okay, ADC should encode this instruction. This one should ADCS with R3 and R0 should equal this, and it doesn't. Why doesn't it want to equal? Oh, yeah, hexa. Okay, perfect. So we got encoding right, and now we can go on with the test case. That would be the first one, right? ADC. And the spec file. Yep. Can remove this from the list, and then we'll only have one more to go. Let's close this console so we have more screen space. Now we can just choose any random pair of registers, ADC, R5, R4, R5, R4, and that should be ADC. Yes, okay. Yep, it says ADCS, so ADCS. And then let's say that R4 equals 55 and R5 equals 66. And then the result should be R5 should have what's the sum of these two numbers? 121. Don't tell anyone I did this. It's between us. Okay, so this should be the result, but we also want to add a carry. So let's set a carry to true, and it should be equal 122. And the result is not negative, it's not 0, there is no carry, and there wasn't any overflow. Not an interesting test case, just a basic one. And now we can implement the instruction ADCS. There is only one encoding. Yep. Cool. And let's first of all copy again this sequence of bit and add an else here before we forget. So if the opcode equals this long thing shifted by 6, yep, and we need to find RM and RDN. RM shifted by 3, and this is just the 3 LSBs RDN, and then the result is basically this one, and right value should be consts. Why are they lets? We're not changing them. Let's make them all consts. Okay, so left value, and this is right value. It doesn't really matter. We are just adding two values plus this.c, then 1, otherwise 0. That's the add with carry. And then this got the result, and then I think these are all the same. And then for the overflow, we actually so this is right value, and we actually have to it's 32 bits, so we can just look at it. We can just probably do it like that. So if they are both positive and the result is negative, but then we have the carry, yeah, or in this case they can also be negative, both of them. If they are both negative and the result is positive, then we had an overflow. Okay, let's add another test case. So this passes. Let's add another test case just to play around with this overflow flag. So let's say we had this very big number and we added 0 to it. So now, but we also added carry. Yep. So that's the signed int. Okay, but why all uppercase? I don't know. Okay, and we added this, so the result should be basically this, right? But it's negative, it's not 0, and we did have an overflow, so why is it false? Let's see. So left value is 66. Oh, let's focus on this one. So left value is 0. Yep, one of them is 0. Right value is big. Okay, so I guess it should be greater or equal to 0. Probably. Yeah. So yeah, we caught an edge case where one of the operands is 0 and we didn't deal with that. Cool. So we got ADC working. Cool. ADCS. Let's remove this from the filter, so all the tests are running. And finally, we got this UXTB. I have no idea what it does. Let's find out. Unsigned extend byte extracts 8-bit value from a register. 0 extends to 32 bits. Okay, it doesn't sound too complex. Cool, and it also doesn't update the flags. So basically, 0 extending. Sign extending, we already sign extends, right? Oh no, wait a second. We extract 8-bit value from a register, 0 extended to 32 bits, so no sign here. Nice. So what do we do here? So we have RM and we are rotating it by 0, which doesn't do anything. We just take the lower 8 bits and copy them to another register. Super easy, cool. I like this instruction. It's my favorite so far. Okay, let's start with the assembler for this. So let's start with this test case just because. We UXTB so this opcode. R3 should equal, but I deleted the opcode. No, I never copied the opcode. What was the opcode? It should be equal this UXTB, and let's create that opcode. Export function opcode UXTB, and we get here RDRM, and basically that's the long string of bits. Cool, and then that's RM or D. Cool, and let's see if this passes. Yep. Okay, so we have this function. We can now write the test case. Okay, let's quickly create a test case for this function instruction, and this is the opcode. Oh, we don't need this. Cool. We have the function to create the opcode for us. So that's opcode UXTB. That's, yeah, R3 is fine. Actually, let's make them different just to make sure we don't miss something in the implementation. Okay, so let's say that R3 starts with this value 1, 2, 3, 4, 5, 6, 7, 8, and then we execute the instruction, and then we want R5 to have just this low byte. We can delete this, and why does it pass? Interesting. It doesn't seem to match any of the instructions here, so oh, right, we didn't write an assertion, we did an assignment. Yeah, bug with the test. Okay, so yeah, now it fails as expected to equal. Now it fails as expected, and we can implement this instruction. That's UXTB, and copying those bits again. Okay, we have RM, RD, and then we say these dot registers RD equals these dot registers RM, and just take the lower byte. And why doesn't it pass? Because we are missing a character. Okay, cool. I think we did it. We finished, or we almost did it, and then yeah, we finished implementing all the missing instructions. That one was a piece of a cake, the last one. And finally, we have the code. It runs, it does something. I'm not sure yet what it does, but it reads from this register, and it seems to be doing stuff. I don't know. Let's go back to the code and figure out what it's doing, and see if we can get some prints going on. So first of all, it's reading from this address, and I don't think we did we? Oh yeah, this is the register that tells it if we are if the UART is busy or something like that. Let's just refresh my memory. So that was on the RP24 peripherals, UART registers, and this is the UART base. So maybe we should have this as a constant. Okay, don't we have it somewhere already? No. Okay, cool. And then that's UART FR, UART flag register. So const UART FR is this. And then we can replace this magic constant with UART FR. Cool. This is the flag register. We are reading from the flag register, and let's try to correspond that read to the source code. So this is the 3C6. Yep. No, that's 13C6. 366. LDRB, that's reading. We are testing, and then if it's not equal, then we are going back here. So this is like, I think we hit that loop last time where we were like waiting for like the code is waiting for the UART to be ready, and it's repeatedly reading this flag and testing. If it's 1, then it's just busy waiting until it gets into 0. And in our case, we can see that it sort of falls through to the next instruction, 3cc. So basically this part is good, but then I guess it's doing something else, because actually maybe is it writing anything? Let's try to see. So let's try to correspond the code here with what we see here. So we'd call UART init, and there is this call, and then GPIO set function and GPIO set function. And right now we just ignore these BLs. Maybe we'll implement, so the code for BL is just skipping this opcode that was inside RP BL. Yeah, you can see it just skips this code for now, this opcode. But after that, we have all of this code, which is probably the inline code for UART puts row, UART puts, and UART puts. And that's like the part where they are looking at this register. So yeah, that's like the first loop that tests this register. Maybe let's have a look at the source code of this UART puts row, just to make sure it does what we think it does. So this is the code, and basically it just calls UART write blocking and gives it the address, the memory address of the character, and tells it to write probably 1 character. And UART write blocking, what does it do? And this is, by the way, the Pico SDK. You can find it on Raspberry Pi's GitHub. Yep. Yeah, it's just doing if not UART writable, then tie loop contents. I think I've seen this before. Just a macro that does nothing. Yeah, as far as I remember, it doesn't do a lot. Yep, just nominally empty function, but can be modified for debugging. So if at some point we want to debug then those tight loops, then we can put a debug print here or something like that. Anyway, so where have we been before? So yeah, so UART blocking. Yeah, so basically I guess this UART is writable is just yeah, it just looks at FR and texts this TXFF flag. That's TXFF. It checks if the FIFO is full, and then if it's not full, then UART is writable. So that's what this loop here does. That reads that's reading the flag, checking the bits against R1. R1 is 32, so that corresponds to the 5th bit. And then just going back, so that's the while loop that calls UART is writable. And once it's writable, we are just calling UART get HW arrow DR. So DR is probably another register. Yep, URDR. And we are writing the next character there. So that's probably what the next code is going to do. Move R365. I think this 65 is the A. This is the character that we will write. And then we are storing this R3 into R2. And if you remember, R2 is like this loaded from here. It's the base UART address. So R2 plus 0 is actually the address of URDR. So this is like, where were we? Yep. So this is like the equivalent or the equivalent code, basically writing the value of R3, that's the A, into this memory address, into the URDR, and then we are loading this value into R3. What's that value? I guess this is doing this src++. But anyway, in order to get to intercept these writes, we need to listen to the value of URDR. Let's do that. So let's go back to our code and go to random blink, and now define URDR, and we know it's the offset, like we have seen from the datasheet, is 0. And just like we have Redux, let's create write hooks that will let us intercept writes to memory, and CPU write callback instead of read, and the write callback doesn't return anything, and it gets an address and a value, so the value that was written to this address. And then whenever we write, we need to call this write hooks, and let's see what happens with the writing. So we have this write uint32, and we actually have something that already sort of intercepts writes to the GPIO pins, and eventually we will replace it with this kind of write hook, so it won't be hard coded. But right now, let's just worry about I think it's not in the, what's the SAO start address? Yeah, it's not in the SAO anyway, so it's like in a different address space. So with the read, we just did this else. If we didn't intercept the address, then so this is else, and this is another else. If we didn't intercept this address, then just call this .write hooks.get address, and if we have hook, then we call hook with address and value. And at some point we may have to worry about writes that are less than 32 bits, but right now we basically don't care. Maybe we'll add another argument to the hook that will specify the size of the write or something like that. Okay, so we have this write hook, and then we can say mcu.write hooks.set UART 0 base plus UART dr equals and then it gets address and value, and we can say console.log UART value and print the value. Let's see if this works. Starting the code. And yep, we are seeing some values on the output, 66, 65, looks pretty promising. So the next thing I'm going to do, let's just remove those debugging prints for a moment. And let's take a look at the definition of URDR. So basically, let's see what does URDR do. So URDR, it has a few bits, and there are like a few bits that are read-only RO that tell us about various conditions of the UART, like if there was some kind of FIFO full or any other kind of error. But then the lower 8 bits are like the data we read or transmit to the UART. So in this case, we just need to get the lower 8 bits. And let's also print it as a ASCII. So UART send. Okay, no, I want to print it as ASCII. So string.from charcode. Cool. And npm start, and hopefully we'll get some UART output. So we see A, B, and a space. Okay, why do we see a space? So A and B, I think they are corresponding to these prints in the code, which is quite cool. And maybe we're seeing this space. Oh, this is so exciting. It's finally working. We are getting a UART output from the simulated code. And we didn't have to do a lot, like we implemented 20 instructions or so. Anyway, let's keep running it for a while. Instead of 60, let's run it for like 20, 40 instructions. And let's also remove all those reading from debug prints, so we don't get all this clutter. Let's just hide them for now. Actually, we can remove them altogether. We used them when we had a problem with the LDR, but now we fixed that. And npm start, and hello UART, yep, it's working. And let's just run it for a few more instructions so we can print the /n at the end. 218, yep. Yeah, so finally we have debug output from the program. We can we can just get the output, and then we have a new unimplemented instruction, which is pop. We still haven't implemented pop, but we don't have to worry about that right now, because I think at this point it's a good point to uncomment for debugging. Okay, at this point it's a good point to commit the changes, so let's just have a quick review. Okay, and oh, thank you, Mark. I'm so happy to see this. Congratulations. Yeah, thank you, Steve. UART party. more instructions plus UART working, coded during the third live coding session. Yeah, I think we also set a record. This is the first time we have a commit. I think it's 1 hour 45 after we started the session. So it's the quickest time to commit and finish a feature that we have. Thank you, Nekari. Yep, a few more instructions and the UART working. And while I'm committing this, do we need, yeah, we did this. While I'm committing this, I would love to know, to check with you, how would you like to proceed from here? Because we have, let me write it down. We have a few things that we can do. We can start looking at, you know, implementing. We can just like, so we can start like implementing better abstractions. So basically, e.g. class to handle GPIO. Thank you for all the comments in the chat. So, or class to handle UART. So basically, whoever is going to use the simulator won't have to just do this read hooks and write hooks. They will have a better interface to set up the UART, to get the received bytes, to do all of this. So that's one thing we can do. Another thing we can try to do is to get the bootrom working. I don't know how big that would be, but basically that would mean that we have the full boot sequence that the chip has, and we don't have to worry about you know, figuring out where to start executing the code. And for that, we'll obviously need to get BL done. That's the bare minimum. So we would need to get BL done in order to get the bootrom working, and probably a bunch of other instructions. And then what else can we do? I think these are like, there is probably another thing we can do, but I think it might be too early, like release an early version of the package. And for that, we would need to tidy up a few things to, you know, set up the I don't want to save it. To set up like how to compile the code and how to deploy it to NPM. That's the Node package manager, so it can be consumed by Node.js and by web applications. Oh, and we can also create a small web application for the simulator, even though at this stage I'm not sure if we have enough things for web application. Like, I think again we would need to get a bootrom working to get into this magical feeling where you can just, you know, drop a UF2 file and get an LED blinking or see serial output, because right now we are just faking it and just going right into main. So yeah, of course we can add a mock sensor Nekati once we have like the class. I don't know which sensors it has on board. If you can find information and share it, then that would be awesome. But they probably need at least the GPIO, and maybe we also need like I2C or analog. I think the ADC, there is, I see a built-in temperature sensor. So we would probably need to implement those peripherals first. So in order to get to work with the sensors. And I think before we do that, that would make sense to get at least these two done. So I'm thinking I would love to hear what would you like us to do next, to go with the better abstractions or to get the bootrom working. I think my personal preference would be to get a bootrom working and then work out the abstractions, because it's getting the bootrom working will sort of let us close the loop where we have a hex file or a UF2 file, and then we can just drop them in the simulator and everything works. But that also could prove as a very ambitious task, because they might be using all sort of obscure opcodes that nobody else needs. If I'm not mistaken, for instance, the bootrom is doing all kind of stuff with the USB if you set it into bootloader mode, and it also checks like which CPU core is currently active, and it could be initializing some of the peripherals. So there might be a bit of work there. So I'm waiting for the feedback on the chat. While I'm doing it, let's just let's just wrap this UART with something more useful. So let's create a new class, UART.ts, class RP UART, and the RP UART gets let's call it private RP24. It gets the instance of the RP24, and then at the basic thing this class will do, this is just like a sketch of implementing a better abstraction for the UART. So instead of having all of those in the main program, UART will take care of them. And then it also gets UART base address, which is by default the UART 0. But then if somebody wants to use UART 1, they can just, let's explore those. The UART 1 base. So where is the UART 1 base? That's the UART 1 base. And then then the constructor would just set up the hooks. Let's call it MCU instead of and then base address. Cool. And then instead of like printing it, let's add a method private on UART byte or on byte. It gets value number and it returns nothing. Then we call on byte, and then it's up to this dot on byte, and this is not initialized, so we need to make it optional. And then this operator is pretty new to JavaScript. It just says if this is defined, then call the function normally, but if this is undefined, there is no value here, just skip this call, don't do anything here. Just it's called the safe navigation operator, I think, or Elvis operator, and it's just a nice syntactic sugar. And now we can refactor our program to look a little bit more const UART is new RP UART. Okay, and then we can say that we can remove all this clutter from here. UART dot on byte value. Okay, so just print the value, and we don't need the read hook. Why isn't it happy? Oh, byte is we need to assign it. Okay, cool. It wants the type for value, let it be. Does it need it? I think it can. No, it needs it. Okay, cool. Oh, because we haven't imported the class. And now we don't need a type because it can infer it from the definition, and this should be public. So others can use this API, and this gets the MCU, and that's it. We have a bit nicer abstraction over UART. Eventually, we will want to string that from char code. Eventually, we will want to implement a better like UART and actually implement this flag with the FIFO and test for like use the baud rate to determine when the when we have finished sending the current byte, and only then clear this flag and create unit tests for this class. But for now, it just does the trick and it lets us move forward. So cool, let's commit this, refactor, UART, move to own class. Cool. Okay, now it's a good time to read what Steve says. The bootloader won't be most interesting. There aren't any obscure opcodes in ARM, especially not in thumb mode. Cool. So yeah, so I think we did a small part of this, and let's try to get the bootrom working. Obviously we won't finish that today, but I just want to just do some initial exploration, so next time we can jump right into it. And hopefully get this to start from zero. We also have some kind of technical debt that we need to fix before we can get a bootrom working, and that is that the PC should always, like the flash should be mapped to 10 million something. Right now we are starting from this address, which is not really this address, so we are sort of cheating. Let's see if this works out of the box right now. I think we handled that. No, it doesn't. So we need to handle that in the code to make sure we are reading from the flash when we are giving this kind of address. So let's go to the RP2040 and let's see. So yep, we are just reading like that. So instead of reading like that, we could probably use read uint 16. And that would also allow us to execute code from the RAM instead of just the flash. And this may cause the test to fail, because the tests, they all assume that the code is loaded at 0, so we'll need to figure that out as well. But let's first of all see if epic failure, what happens. Video in 16. Oh yeah, why do we divide PC by 2? Do we need to divide PC by 2? Oh, because we are, yeah, the original redo in 16 was getting an offset in words, and now we this one is actually getting offset in bytes, so we don't need to divide by 2 anymore. And yeah, now the code works, and now we get proper addresses. Some instructions are not implemented yet. Interesting, but it still runs, so I guess we shouldn't care about that too much right now. And interestingly, the tests are still passing, and I think that's because we are cheating again here in this read. And yeah, if it's less than the flash start address, we are actually still reading it from the flash, but soon we will read it from the bootrom. So that's one thing that we will need to fix as soon as we start using the bootrom. But first of all, let's commit this, fix RP2040, use correct flash addresses. Cool. So a small fix. And now, once we fix that, let's take a quick look at what the bootrom is. So fortunately, the bootrom is available also on GitHub. I haven't seen if the binary is available. So if anyone here has a Pico and wants to try extracting the actual binary from the Pico, then that would be cool. What they are saying here in the README, this is the B1 version of the blah blah bootrom. It was built using la la la. Note that the Git revision info including in the bootrom on chip does not match this branch. No idea why, but they may have like used a different repository with a different history. So that could be the same code but with different history. So that could be the reason. Anyway, if you check the Hackaday page, I posted, let's go over there. Yeah, that would probably get us Emulator to the right place. There is an update that explains how I compiled it. It turned out to be pretty easy, but pretty straightforward. But if you want to check it out, it's called Building the Bootrom, just installing dependencies, checking the repo and running a few commands and then waiting a few minutes or moments. I don't remember. It was a week or two ago. Anyway, so this is the source code for the bootrom, and then it builds similar to the examples. And we also get this disassembly file. And just like with the examples, and we can actually see the code here. And if you go to the beginning, we can see there is like this vectors array, and it contains a few things that looks like pointers. So these are like, we know 00 is like bootrom addresses, so these are pointers. And this is some kind of memory address, and I think this is mentioned in the somewhere. In the documentation, the format of these vectors. Where are you, dear vectors? Maybe here, alignment. Maybe here. I've seen it once. So probably not here. Yeah, the architecture relative to a table that is fixed at 0. So yeah, this is the address space, but what are the actual vectors? Vectors. Yeah, I think I've seen it in the past, like at some point where the vectors are defined. Maybe it's vector table. Oh yeah, there we go. So yeah, so you can see that the vector table, it has the initialization value for the stack pointer on reset, and the enter point for all the exception handlers. So this first value is the SP main. This is the value, the reset value of the main stack pointer. And as you probably remember, maybe not, there is like this register, which is the stack pointer. So the first thing we do when we load a bootrom, we just initialize the stack pointer to this value, and then there is this table, and it shows us that this is the entry number 1. The next entry in the table is the reset vector. So basically that second number is where we jump when we start like executing. So this is the address, and this is actually pretty straightforward so far. So the first thing we'll do, we'll load this value into SP, then load this address into PC, jump to this address, and what's this address? EF, where are you, EF? So, okay, so that's one thing about addresses in thumb mode. The least significant bit is always set. So when reading these addresses, we should actually ignore that bit. So it's not actually EF, it's EE. And the reason it's set is that the role of that bit in PC is to determine whether we are running in thumb mode or not. And this MCU only runs in thumb mode, so it's always set. But in other ARM MCUs, this bit might be clear when running in normal ARM mode with 4-byte instructions. Anyway, so we should remove or ignore the least significant bit here, and then jump to this address. And this address is the address of the start function that is the entry point of the bootloader. And then we can see it already has like some kind of checking something, loading a value from this PC460. What's there? Not sure what's there. Oh, that's this value. Oh, 2PC. From 2PC, so loading this value, D0000. Yep. And then after that, we are async task. We are loading from that, so that was this plus 0, so we are loading the value from that, comparing it to 0, and then if it's not 0, we are going to wait for vector, otherwise we are going to NMI. So I think, I'm not sure, we'll take a look at the source code in a moment, but I think this might implement this logic where it checks. So this has 2 cores. Actually, we should have looked at that first. There is a whole system about the bootrom, a whole section. So it tells us what the bootrom has, and you can see the first thing that happens in the bootrom is which core am I. If I'm core number 0, then it's doing all those things. Otherwise, if it's core number 1, it sleeps until given entry point. So basically it's waiting. And I think this is what this start function does. And in terms of instructions, we already have most of them, I think. We have LDR, CMP, BNE, BL. And let's try to find this method in the actual bootrom. That's bootrom. And I guess the runtime defines start. Yep, here is start, and then this is the code before compilation. Let's put them side by side. So, yeah. So global start, and you can see that this is actually this. It loads this value, and it reads the SAO CPU ID offset, which is probably 0, compares it to 0. And if it's not equal, then wait for vector is probably that loop that keeps the core busy until it like sleeping or something, until it has something to do. Otherwise, we are jumping to NMI. I don't know what NMI does, but yeah, I think other than BL, enabling clocks, yep. Other than BL and probably BX, which is just for returning for function. Oh, MVNS, I don't think we have that one as well. So yeah, so there are a few instructions missing here and there, but yeah, I think I can recognize most of the instructions, which is cool. Anyway, I think we will leave running the actual bootrom code in the simulation for the next week, and then figuring out if there is anything that we should ignore. If I'm not mistaken, the bootrom itself at some point is trying to load data from the flash. So imagine this, the bootrom is running on the chip and it still doesn't have, the chip still doesn't have the flash configured. So the bootrom itself is sort of trying to figure out which flash is connected to the chip and initialize it and do everything. So you can see that it loads like 256 bytes from flash. It checks, it validates some checksum that they have, and if the checksum pass, then it enters flash second stage. Otherwise, it does some loop that tries to probably figure out the correct clock parameters for the flash. So it can work with different kind of flash. And then if it doesn't succeed after 2.5 seconds, then it starts the crystal oscillator and starts the USB mode, device bootloader mode. And it also does this if there is a flash CSN, that's probably one of the pins or something like that. So this determines whether we are going to do the boot or going to do the USB thing, and we definitely want it to go through this like path. So yeah, we'll have we have a lot to look at for the next time, but at least I hope that you already have the general idea of what we are going to do. Anyway, I think it's been a pretty fruitful session, and now you can just go to the repo, clone it, npm start, and just stir the bytes and enjoy them. Or if you feel adventurous, you can also go to hello UART and recompile it with more code and run it in the simulation and see what happens. Suddenly it's nice to start to get some output. And if you just want to help out and make it a little easier for us in the future, then you can just update the tests and tidy them with those opcodes like we did here, and send a pull request. That would be super cool if you do that. And that's it. So I hope to see you next week. I hope you enjoyed this session, and as always, you are invited to the Discord chat. Let me share the link. And we have a special channel for this project, so you are invited to just chat with me during the week and with other people here, and ask questions, or if you have any ideas or requests, and I will be happy to know about it. Anyway, have a great week, and yeah, let's do the bootrom next time. Bye bye.